quote a great philosopher named Homer, beer. I guess I should have said Homer Simpson. It has been proposed by some archaeologists that it was beer that built civilizations. Well, perhaps some wobbly ones anyway, in that our ancestors started to domesticate cereals not to make bread, but to brew beer. Priorities, priorities. The origins of beer likely go back to the early Neolithic period, about 9500 BC. Beer is known to have been consumed in ancient Egypt, and chemical evidence of this wonderful liquid has been found in Godin Tepe, dating to 3500 to 3100 BC in the Zagros Mountains of Iran. Some of the earliest Sumerian writings reference beer too. It is thought that the prayer to the goddess Ninkasi also served as an oral recipe for brewing. Just imagine if your favourite hymn also contained information on how to mix a really good gin and tonic. Isn't it wonderful that something so good and refreshing could come from something as humble as grass? Well, barley to be specific in the case of beer. Grasses are angiosperms, flowering plants, but unlike a lot of angiosperms, almost all of them rely on wind rather than insect pollination. True grasses of the family Poaceae, Graminae of the older parlance, are characterised by having very small to almost microscopic flowers arranged in a spike-like structure with long leaves that have parallel veins. And of course, they produce fruit in the form of grain. Specifically, they grow from the base rather than the tip, which means they can keep on growing even if grazed. The grass family is the most economically significant plant family today. They include cereal crops like maize, wheat, rice, and our old boozy friend barley. They are also used as a construction material in the case of bamboo and thatch, and some, such as sugarcane, are fermented to make ethanol biofuels. Altogether, it is estimated that there are probably around 10,000 species of grass. This is an important group of plants. So in this lecture, let's consider grass. Is it a new plant? When was it that the grassy carpet started to spread? What triggered the spread of our grassy planet? How significant have grasses been on the evolution of animals? Before we move on to our investigation of grasses though, I'd like to introduce you to a paleontologist who had to fight the sensibilities and prejudice of the late 18th and early 19th century to take part in science and scientific discovery. At this time, science was generally regarded as the pastime for genteel people, people with the correct family background and breeding, and more importantly, a ready supply of cash. Oh, and another thing, you would most likely be a man too. The paleontologist in question is one Mary Anning, daughter of a cabinet maker in the pretty little town of Lyme Regis on the Dorset coast of England. From the cliffs close to her home, she would collect fossils that were instrumental in developing our understanding of Mesozoic marine reptiles, and in a broader sense, our understanding of how the biosphere has changed dramatically over time. However, because of her position and gender, she never had a forum to directly present her discoveries to her peers. She did become quite famous for her discoveries though, and this is one of those discoveries I want to consider in this lecture. In the abdominal area of an ichthyosaur, that's a streamlined marine reptile that kind of resembles a modern dolphin, she would discover structures called bezoar stones. Bezoar stones were much sought after as they were believed to have magical properties, including the ability to cure any case of poisoning. Mary noted that when broken open, these stones contained the fossilised bones and scales of fish and sometimes fragmentary remains of other marine reptiles. In 1829, another famous geologist and friend of Mary's, William Buckland, proposed that these were in fact fossilised faeces. Buckland named them coprolites, from the classical Greek kopros, meaning dung, and lithos, meaning stone. He went further in his investigations though. He found spiral marks on the coprolites that he suggested had been produced by the ridges of the ichthyosaur's intestines. He also thought that very black coprolites might be the result of ichthyosaurs eating belemnites, a kind of Mesozoic squid with their ink turning the poop black. Coprolites are extremely valuable to paleontologists. Although it is not always possible to tie coprolites to specific animals, you can certainly tell what the creature was eating. They also provide a wonderful survey of the possible animals and plants that lived in a particular environment. For example, this is some poop I found while visiting Indonesia, produced by the Asian palm civet. Some braver coffee addicts than me harvest the partly digested coffee beans from this to make kopi luwak coffee. To be honest, I've never really been that tempted to try it. In coprolites though, much of the original organic material has been replaced by minerals like calcite or quartz. In 1842, John Stevens Henslow, a professor at Cambridge University, developed a technique for extracting phosphate from coprolites, and the mining of fossil poop became a big business in Cambridgeshire. The phosphate was used for the British fertiliser and munitions industry. Incidentally, Henslow is famous for another reason too. He was originally listed as the naturalist on the voyage of the Beagle. Famous ship, of course, that was going to survey South America. His wife persuaded him not to go, and so Henslow suggested a young naturalist of his acquaintance to take his place, one Charles Darwin. And that, folks, is how history is made. But why am I banging on about fossilised poop in a lecture about grass? Well, until recently, the general mantra regarding the evolution of grass was that the first grasses evolved long after the dinosaurs became extinct at 66 million years ago. The oldest fossil grass came from Tennessee, dated to about 55 million years ago. There were hints of earlier grasses from fossil pollen, but grass pollen is very difficult to tell apart from non-grass pollen. As such, images of dinosaurs striding through grasses were generally regarded as incorrect renderings of the Mesozoic world. A common exam question for students of paleontology would be, what's wrong with this picture? A discovery by paleobotanists of Lucknow and Punjab University, India, would turn these ideas around though. They found coprolites from the late Cretaceous towards the end of the dinosaurs' reign on Earth that appeared to contain phytoliths. Phytoliths are tiny silica structures found in the leaves of certain plants. They help give grass some of its structural support and may also act as a defensive structure, deterring grazing by animals. They called in phytolith expert Caroline Stromberg, currently at the University of Washington. On analysing the phytoliths, she identified them as coming from various grasses representing at least 5 species. This is significant because, in addition to showing that they existed at the time of the dinosaurs, the phytoliths demonstrated that grass species in the late Cretaceous had already diversified. This means that the antiquity of grass was a lot longer than anyone had suspected. Stromberg has suggested that this may have pushed back the origin of grass to about 100 million years ago. We shall see later how right she was. Dinosaur fossils found in close association with these coprolites come from a rather poorly defined but still rather exciting group of sauropod dinosaurs called titanosaurs. The titanosaurs contain some of the largest creatures to have ever walked the earth. For example, Argentinosaurus, weighing about 83.2 tons and was around 30 meters long. There is a strong possibility that the smoking poop gun, if you'll excuse the analogy, lies with the titanosaurs. These dinosaurs would have dined on a wide variety of vegetation, with other flowering plants, cycads and conifers forming part of their diets. It would appear that they were browsers, nibbling leaves from trees and bushes, but also grazers, mowing grass, which might explain their wide mouths, similar to many modern grazing animals today. The possibility of grasses at this time might also explain why small mammals called Gondwanatherians, that were scurrying around the feet of the dinosaurs, possessed high-crowned or hypsodont teeth, like the teeth of modern horses and cows. These teeth are thought by some to have evolved as a response to the gritty phytoliths in grass, although, as we shall see, the grass and teeth relationship has been questioned recently. As it turns out, we have recently found evidence of even older grass dated between 97 to 100 million years ago. That's the mid-Cretaceous, preserved in amber from Myanmar, Burma. This is research led by Dr. George Poyner of Oregon State University, who is one of the world's leading experts on amber and the fossils found in it. As we dealt with in an earlier lecture, amber was originally tree resin. As it runs down trees, it picks up and beautifully preserves insects, small vertebrates, plants, and a whole bunch of other things too, associated close to or actually on the tree. Dr. Poyner and his colleagues found a beautifully preserved grass floret, preserved in amber, and on its tip was an interesting dark structure. When investigated, this was found to be an extinct species of parasitic fungus called Paleoclaviceps parasiticus that is likely closely related to a group of fungi that today we call ergot. Ergot may have a special relationship with grass. It tastes bitter and would deter grazing by herbivores. The problem is, if you ingest enough of the stuff, it can cause serious side effects. In cattle, it can cause a condition called paspalum staggers, where the animal's major muscle groups will tremble, they become clumsy, and if they try to run, they tend to fall over. Humans can also suffer from ergot poisoning. It's called ergotism. It can cause hallucinations, irrational behaviour, convulsions, and vasoconstriction leading to gangrene. It is possible that many reports of sudden deaths of large groups of people in villages and towns during the Middle Ages may have been caused by people eating rye bread contaminated with ergot. Indeed, some historians believe that the great fear associated with the French Revolution in 1789 may have been fueled by peasants having to eat wheat that was contaminated by ergot. And in 1976, Linda Capriel suggested that the hysterical behaviour of the women during the Salem witch trials may have been caused by ergotism, although this hypothesis has been criticised much in recent years. One of the reasons why ergot has such bizarre effects on animals is that one of the alkaloids extracted from this fungus are lysergic acid derivatives. That is the same stuff from which LSD was synthesized by Swiss chemist Albert Hofmann in 1938. Herbivorous dinosaurs were probably vacuuming up ergot as well as grass during the Cretaceous. Not that dinosaurs were high on LSD, but you could imagine some of the ergot alkaloids having serious effects, and no one wants a giant dinosaur stumbling around the landscape. On a planetary scale, probably more significant than the date of evolution of the first grasses, though, is the development and evolution of the ecosystem that they would create. The ecosystem we call grasslands, or more formally, the grassland biome. There are many different types of grassland. There are savannas and veldts of Africa, and here in North America we have the prairies. There are the pampas and llanos in South America, and the steppes in Eurasia. Today, grasslands cover a whopping 40% of all our planet's land surface. As grasses are mostly annual plants that die every year, they develop large and deep soil profiles. Grasslands are generally associated with dry but not desert conditions, receiving about 20 to 36 inches of rain every year. Because of their higher rate of turnover, grasses and grasslands can support a large animal population, unlike trees and shrubs or forests where a lot of the useful nutrient-rich material is locked up in the plant. Another feature is their tendency to burn, creating grassland fires. Rather than being detrimental to grasslands, fires may be an important part of some grassland ecosystems, removing trees and shrubs and allowing grasslands to spread. But when do we see the advance of this biologically and economically vital part of today's biosphere? Let's look at the history of the planet's overall flora, following the extinction that wiped out the Mesozoic world, including the dinosaurs, around 66 million years ago. As we have noted, grasses existed during the Cretaceous, but they were not a particularly significant part of the Earth's flora. Even after the Cretaceous, in the first two periods of the Cenozoic era, the world was mostly tropical, warm and wet, and mostly covered with forest. Most of the mammals that existed in those ancient forests were small, a much better strategy for a dense forest environment. Not all creatures were tiny though, with relatives of the dinosaurs like Gastronis, a large flightless bird, standing some 2 meters tall, probably terrorizing the local mammal population. A beautiful snapshot of the world at this time, about 48 million years ago, can be found in the fossils of the Messelpitz deposit of Germany, and although many modern plant taxa are present, there is not a single species of grass that is known from this very well documented plant community preserved there. Grasses did not dominate, at least not yet. By about 40 million years ago, as the Eocene was drawing to a close, the Earth's climate started to change, becoming much drier and cooler. Forests gave way to woodlands and eventually into chaparral and other scrub formations and deserts. Still lacking, though, were a major component of grasses. By the time we move into the Oligocene, this desert scrub starts to give way to grasses and their deep soil profiles. By the late Oligocene, we have evidence of the grassland biome and an association of grassland-adapted mammals spreading across North America. But what would be the trigger that would allow the development of our grassy planet? For this, we need to look at the way that some plants conduct the business of photosynthesis. Around 95% of land plants and some grasses use what is called the C3 metabolic pathway. It is named the C3 pathway for the 3 carbon molecules that are produced as the first product of carbon fixation. This form of photosynthesis probably evolved way back in the Paleozoic. Many grasses and some other plants use a C4 metabolic pathway, as the first molecule produced in this case has 4 carbon molecules. Some C4 plants possess a particular arrangement of cells called the Kranz anatomy, where the vascular tissue that transports the products of photosynthesis, that will be sugars, is surrounded by 2 rings of cells. Now, without going into too much detail of the biochemistry, the Kranz anatomy provides a site where carbon dioxide can be concentrated in the inner ring of cells called the bundle sheath. This effectively, charges the cells with carbon dioxide for photosynthesis, which means that C4 plants can operate at lower levels of atmospheric CO2 than a C3 plant can. This imparts another advantage though, because C4 plants don't need as much CO2. They can afford to keep their stoma, those are the surface pores that allow gas exchange between the plant and the atmosphere, to be closed more often than C3 plants, since C3 plants need to be gulping in more CO2. This means that in dry conditions, plants like C4 grasses have a selective advantage. For example, at 30 degrees Celsius, C3 plants lose 883 molecules of water per carbon dioxide molecule that they fix, but C4 plants only lose 277. This makes them perfect plants for arid conditions and for the spread of grasslands. Today, C4 plants make up about 5% of Earth's plants' biomass and around 3% of known species, but account for a massive 20 to 30% of terrestrial plant carbon fixation. C4 plants in grasslands are so efficient at drawing down CO2 from the atmosphere that some have suggested that they could be a biological solution to reducing our current rising levels of anthropogenic carbon dioxide. The C4 pathway runs about 6 times faster than the C3 pathway, and it is this efficiency that has inspired the C4 Rice Project. This initiative is attempting to produce rice, which is naturally a C3 plant, with a C4 metabolism. It is predicted that this would double the rice yield while using less nutrients and water, one possible weapon in the war against future global famine. It is only in the past 10 million years, though, that C4 plants have become such an important part of the biosphere, with a remarkable C3 to C4 plant transition occurring globally between 8 to 4 million years ago. This transition is highlighted in the geological record isotopically by studying two of the stable isotopes of carbon, carbon-12 and the slightly heavier form with one more extra neutron in its nucleus, carbon-13. Life in general has a preference for carbon using the carbon-12 isotope, but C4 photosynthesis is slightly less fussy than C3 and will incorporate more of the carbon-13 isotope. This gives us a proxy for the presence of C4 plants recorded isotopically in paleosols, that's fossil soils, or in bones and teeth of the animals that were eating the plants. You can see this here in a diagram adapted from Colin Osborne and David Brearling of the University of Sheffield, who explored the increases in carbon-13 values in paleosols and tooth enamel from North America, Pakistan and East Africa, recording the spread of the C4 grasslands. This change appears to be associated with the general increase in aridity of global climates, favouring those plants with a C4 metabolic pathway that require less water. This increase appears to occur at different times in different regions though. There were probably other mechanisms that played a role in the spread of the C4 grasses too. For example, an increase in charcoal in Pacific cores between 12 to 7 million years ago hints at a greater number of fires during this period. This would favour grasses and grasslands due to their very rapid recovery rates when compared to trees and shrubs. There is also a suggested general reduction in atmospheric carbon dioxide levels during the Cenozoic that may have also favoured C4 plants with their more efficient photosynthesis. Thirdly, the spread of grasslands would encourage more grazers who, in cropping the tops of plants, would favour the spread of grass over trees and shrubs. And it is also likely that there could be a local reason for the spread of grasslands too. But what would set these changes into motion? A possible cause might be found in India, and it's dashed northwards to meet up and dock with southern Asia. The Himalayas would rise as India crumpled into Asia over many millions of years, but during the Miocene, the mountains began to rise in a major way. This thrust vast amounts of rock up into the atmosphere, which started to weather, a process of weathering that involves the transformation of rock silicates into clays by the action of CO2 dissolved in rainwater. This transformation is a process we call silicate weathering. In this way, carbon dioxide is effectively washed from the atmosphere, transported down river systems in the form of clay, and deposited as sediment, causing an overall net drawdown of carbon dioxide. Even if there is no direct link between falling carbon dioxide levels, temperature, and the spread of C4 plants, a general drawdown of CO2 would certainly impact paleoclimate patterns, such as causing the development of a more arid climate, which might favour the spread of water-efficient C4 flora across the land surface. But how has the evolution of a relatively new ecosystem, the grassland biome, impacted the rest of the biosphere? Our traditional view for over 140 years was the evolution of mammals with hycrant hypsodont teeth. This was in response to the spread of phytolith grasses. These large teeth would be an adaptation to eating these gritty grasses, and as such, you could use the presence of hypsodont teeth as a morphological proxy for the presence of grasslands. Unfortunately, this doesn't quite work everywhere. Additional research by Caroline Stromberg on a section of sediments representing 800,000 years of deposition at Gran Barranca in Patagonia, Argentina, has turned this idea around. Hypsodont cheek teeth were discovered in Patagonia dating to around 38 million years ago, which, if we take them as a proxy for grasslands, indicate that grasslands evolved there 20 million years before anywhere else and could represent the cradle of the grassland ecosystem. The deposits are composed of river sediments and wind-blown volcanic ash, probably from the southern volcanic zone in South America. The plant remains, though, do not indicate grassland, but rather a tropical forest dominated by palms. It is possible that in this particular area, hypsodont teeth evolved as a response to the high amount of abrasive volcanic ash and grit in the environment, and phytoliths from other phytolith-bearing plants, like those palms. This effectively undermines the idea that these teeth can always act as a proxy for grasslands. It's not such a simple relationship. In other parts of the world, such as North America, there is a more direct link between the spread of grasslands and the presence of hypsodont mammals in the fossil record, although even here there does appear to be a 4 million year lag between grasslands and the first long-toothed hypsodont animals. But even if the story of teeth evolution in our grazing mammals is not quite nailed down yet, there is certainly a case for a co-association or perhaps co-evolution between grasses and animals. The snout of many creatures becomes broader and flatter to allow more effective grazing, and jaws become longer and deeper, permitting more efficient grinding of plant material. In addition, unable to hide as effectively in grass as you can in a forest, animals start to show adaptations for running. Even if they were not grass browsers, the lower parts of the limbs start to elongate, feet becoming more compact, and muscle mass starts to increase at the shoulders and hips to help power a very rapid and quick getaway. Grass, though, may have had an effect on our evolution too. The spread of grasslands was proposed by some as a reason why our ancestors started to walk upright. Ancestors like the famous Australopithecine Lucy, who lived around 3.2 million years ago, may have evolved an upright posture as an adaptation to look for predators in high grass. Walking upright would have also freed their hands to make tools, which may have set a series of events into motion that would ultimately lead to Homo sapiens and their big brains. This hypothesis, though, was called into question by the discovery of Ardipithecus ramidus in 1994. Ardi, as it was nicknamed, was an upright walking ape-like creature with long arms adapted for climbing trees and feet that had big grasping toes. Ardi, though, had evolved in a woodland environment, not on an open grassland plain. It would appear our family line was pre-adapted to stride through the grasslands. That is not to say that grasses and grasslands have not had a profound effect on our evolution. A very significant part of our own human story evolved on the open grasslands from Lucy right through to modern humans. This is probably the environment that shaped us most. The presence of the grassland biome may have also helped genus Homo move out of the cradle in Africa and start to populate the planet. Possibly the first adventurer was Homo erectus, who is first found in the fossil record about 1.9 million years ago. This was a creature who, from the neck down, would have looked very human, but whose features were still very ape-like. It's been suggested that climatic changes would have opened up the Levantine corridor, a crescentic strip of land along the eastern margin of the Mediterranean, temporarily changing the environment from desert to grassland savanna, probably due to changes in the pattern of the West African monsoon. During green Sahara times, grazing animals would migrate along the corridor, followed by bands of Homo erectus that would spread into Eurasia. This may have started about 1.8 million years ago, with erectus spreading as far as China and the island of Java, facilitated by a carpet of grasses. So the next time you wander past a humble patch of grass, just remember, you are looking at a powerhouse of change that in recent geological years has been a major shaper of the world we live in. Not so humble after all.